Welcome back to electrochemistry. Today I'm going to talk about electrochemical cells and the difference between a two-electrode cell that might seem very simple, where you just have an anode plus a cathode, and what you might see in conventional sort of analytical electrochemistry, which would be a three-electrode cell. And in a three-electrode cell, we have what we call a working electrode, a counter electrode, and a reference electrode. And we'll see how this works, and we'll learn more about these throughout this course. Now, let's consider a simple half-cell reaction. Let's consider one of our typical cell reactions containing zinc, metal, this wire here, in an electrolyte. Okay, say it's in water, and you have zinc 2+, and you have chloride in the electrolyte. And then we have a silver wire, and that silver wire is coated with a coating of silver chloride. Okay. So this forms an electrochemical cell. I have two electrodes. I have an electrolyte that conducts ions, right? And I can hook this up to an external circuit, and I can measure voltages or allow current to pass or apply currents. We can use cell notation to describe this cell as zinc 2+, Cl- in the aqueous phase, AgCl, and Ag. Just to be explicit, these slashes, these indicate a phase boundary. And the phase boundary, in this case, is between the solid zinc and the electrolyte. And in this case, the phase boundary is between two solid phases. So this is a solid, and this is a solid. Okay, so that's how we can depict this two-electrode cell, right? This is a two-electrode cell. And what this allows us to do here is to measure, right? We can measure the voltage across this cell, and that voltage is going to be proportional to delta G for the reaction occurring. Now, this particular cell was set up in a way that this reaction over here is what we call a reference electrode. Now, anything can in principle serve as a reference electrode, but this cell composition, this half reaction composition, is particularly commonly used as a reference electrode. And the reference reaction here is AgCl plus an electron going to Ag plus Cl minus. And that has an E naught of about 0.2 volts versus the standard hydrogen electrode. Okay, so that has an E naught of about 0.2 volts versus the standard hydrogen electrode. And why is this cell a good reference electrode? Well, if you remember the Nernst equation, right? E equals E naught plus RT over NF, ln concentration of O over concentration of R. So this is, of course, just coming from the fact that the delta G depends on Q, right? Depends on the concentration of species in the chemical reaction that you're describing. O and R in this case, well, what are O and R? Well, it's just silver chloride and silver and Cl minus. And so if this reference reaction, if this is concentrated, very high concentration, silver has an activity, it's a solid, activity is 1. Silver chloride has an activity equal to 1. So this potential doesn't depend very much on what you do to this cell. So you can pass a little bit of current through this cell, and you might convert some silver to silver chloride or vice versa, but you're not going to change the chloride concentration much in the cell, and you're not going to change the activities of the solid phases. So that's why this is used as a reference electrode, because its potential is relatively invariant with what you do to the cell. Now, there are other reference electrodes that are commonly used that have similar properties. For example, mercury oxide. Again, you have two solid phases that are in equilibrium with each other, so their activities don't change if a little bit of current is passed through the cell. And this is typically done in KOH. Another one is mercury chloride. And this is done in saturated KCl. Saturated. This is typically 1 molar, or can be different concentrations depending on what your test electrolyte is. And this has a potential, this is called the standard calomel electrode, and you'll use this extensively in the lab in addition to the silver chloride reference electrode, because it's very reliable and easy to procure. And this has an E of 0.242 volts versus the natural or standard hydrogen electrode. And then, of course, there is the standard hydrogen electrode. And these days you can actually buy reversible hydrogen electrodes, a nice little package that actually bubbles hydrogen over a platinized catalyst that senses the hydrogen potential. But we typically don't use these in the lab except for calibration, because they're sort of expensive and difficult to use. But we could write that as platinum in contact with H2 at 1 atmosphere, in contact with H plus at 1 molar. Okay, and this has E, of course, equals 0 volts versus standard hydrogen electrode, which is by definition, right? We define this as 0. Now let's think about a 2-electrode versus a 3-electrode measurement. So let's take the simplest cell we could imagine. Imagine I have my beaker here, and I put some electrolyte in it. Let's say the electrolyte is 0.5 molar H2SO4, so it's about pH 0, okay? So that's our electrolyte. And then I put 2 electrodes in there, 2 sheets of metal, and let's make these platinum. Okay, so it's symmetric. There's 2 platinum electrodes in our electrochemical cell. And then we can, measure voltage across this cell. And we can also apply current to this cell, or measure current. And we can hook this up to a power supply. This is not a potentiostat yet, it's just a power supply. It's going to supply current, and we're going to measure the voltage across this cell. So what are the reactions that we would drive if we did this simple experiment? We have water is the electrolyte. We have H2SO4, so we have H plus in here. We have sulfate, anion. Sulfate's pretty electrochemically stable. So what are the reactions we can drive? Well, let's think about the cathode. So what reaction would happen at the cathode? That's where we would apply our negative voltage to. Well, what's the easiest thing to reduce? Well, the easiest thing to reduce in here is 2H plus 2 electrons goes to H2. So that would happen at the cathode. And this is, of course, is at 0 volts versus NHE. And at the anode, what reaction would occur? At the anode, we would have the oxidation of whatever's the easiest thing to oxidize in this particular cell. And sulfate's hard to oxidize, so that really just leaves water. But the half reaction at the anode would be 1/2 O2, so I'm going to write it as a reduction. We always write these electrochemical reactions as a reduction because it's easier to keep track. Goes to H2O. So this reaction is, of course, going to be driven in reverse because it's at the anode, it's doing oxidation. But here's the reduction reaction. And this is 1.23 volts versus NAG. So to remember those two things. Okay, so now what are we going to measure? So what is the current response to the cell as we sweep the voltage, or another way to say that is as we apply different currents, what voltage does it take to apply those currents? So let's think about that. So let's plot a current voltage curve, I versus V. Okay. So what's going to happen? Well, we need to drive both these reactions simultaneously, right? And the difference between those two, delta E, equals 1.23 volts. So we need a total of 1.23 volts to drive these two reactions. So, I could see that if I added these two half reactions together, right? If I added these reactions together, what would my net reaction be? Well, my net reaction would just be H2O going to H2 plus O2, right? 2H2O going to 2H2 plus O2. So this is the net water splitting reaction, and this takes 1.23 volts to drive based on thermodynamics. So if I look here and I apply a voltage in, say, the positive direction, put positive here. Actually, let's put negative here to be consistent with Barden-Faulkner. There's a sign issue in Barden-Faulkner, and that it uses signs that are opposite to what most of the other rest of the world uses, but we'll deal with that as we move through the course. It's good to be used to both sign conventions. So as we polarize this thing, say negative, this case is actually doesn't matter because they're symmetric electrodes. We know at 1.23 volts, we should start to pass some current, right? And when this current passes, what processes are happening, right? Well, you have to drive a process at the anode, you have to drive a process at the cathode. So, in fact, both these reactions we just drew are happening. So we're doing OER, oxygen evolution reaction, that's this one, OER, plus HER, hydrogen evolution reaction. Okay, so it's doing both of them. And this overpotential here, this is eta, the overpotential we talked about. This overpotential, what's this due to? Well, it's due to driving both these reactions. So this difference here, I'll say eta OER plus eta HER plus IR in the cell. The series resistance of moving ions, right? Because this reaction is consuming protons, this one's generating protons, right? Because I'm doing an oxidation, I'm moving the reaction in the reverse direction. And so the protons have to actually move through the cell, and so there's some IR drop to that. So you get this large overpotential here, but you don't know, right, which fraction of the overpotential is due to which reaction. They're all combined here because it's a two-electrode cell. Now, if I sweep the voltage in the other direction, I'll get a perfectly symmetric response. Negative 1.23. Actually, I said this was negative and that's positive, whatever. Okay, and I'll also have the same problem. I'll have this combined eta that is for all the different species going on. So this I can do this experiment, but it's not very informative because I can't separate what voltage losses are driving what reaction. Okay, and I don't know a priori here if I apply a total voltage, say at 1.5 volts, say I apply this voltage here, what is the relative voltages versus, say, a reference electrode versus some absolute energy of these two different electrodes. So another way to say that, if I have an anode and a cathode, this is the cathode, right? And this is the anode here. And here I've plotted energy up and down, right? This is energy. of the electron, right? The cathode's going to do a reduction. The anode's going to do an oxidation, so it's going to take electrons. And what I'm controlling here is I'm controlling the delta V. But I don't know where these are in any absolute terms. I don't know if the hydrogen level is here or here or here. I don't know where this actual thermodynamics is. So this is a problem with a 2-electrode cell. So now I'd like to talk about a 3-electrode cell that solves these problems and the use of a potentiostat. So 3-electrode cell. In this case, we have our same beaker here. Okay, we're going to use our same electrolyte. We're going to have our same 2 platinum electrodes. So this time we're going to make one high surface area, like a platinum mesh. Okay, in this case, we're just going to have a little platinum flag. Little piece of sheet platinum. Okay, so this one's high surface area. And we're still going to have all sulfuric acid in here, so we're going to have H plus in here, lots of H plus. But now I'm going to add a special electrode. I'm going to add what's called a reference electrode. And we talked about what the reference electrode is. It's something that has a well-defined reduction potential, half-cell potential, that doesn't really change even if a little bit of current gets passed to it. And in this case, let's use a standard hydrogen electrode, okay? So a standard hydrogen electrode is, again, a little piece of platinum. And we're going to have a platinum mesh. And I'm going to move my hydrogen ion down here because it's kind of in the way. Okay. So I have another piece of platinum high surface area platinum mesh. And what I'm going to do is I'm going to take a little tube, okay, and I'm going to put H2 gas in there. And so there's going to be some H2 gas bubbles around that platinum mesh at all times. And what that's going to do is it's going to set up an equilibrium on the reference. So the reference is going to be, the potential of that electrode is going to be set by the equilibrium with this reduction reaction, right? So the electrons here in this platinum wire, the energy of those electrons are set by this equilibrium. So that's going to be an absolute reference. And remember, H2 is at 1 atmosphere, and H plus is going to be at 1 molar. Okay, let's keep it at 1 molar. Okay, and then we have our 2 platinums, and we're going to hook this up to what's known as a potentiostat, which is used to control 3-electrode electrochemical devices. And we'll talk about how those work in a moment. And we're going to hook those up there, okay? Hook those up. And we're going to call this platinum flag, we're going to call the working electrode. So this is where the reaction that we're interested, that we're going to study, is going to take place. So this is the working electrode, okay, going down here to my platinum flag. And then the counter electrode, we're going to call this one, going to my high surface area platinum. And then the reference electrode is this green guy going to my platinum mesh, where the potential is controlled by this reference reaction. Okay. So now that we've done that, we've set this up, how can we think about now the reactions we're going to measure? Well, let's draw a curve. And actually, before I do that, I want to say a few things about what the potentiostat does. So we'll talk about how this works in a moment, but a potentiostat, we'll abbreviate that POT, it controls the working electrode potential versus the reference electrode. Okay? So the potentiostat controls the potential of this electrode, the working electrode, versus this reference potential, which is set by this chemical equilibrium we just talked about. So voltage losses at the counter electrode, okay, voltage losses at the counter electrode are not included in what you measure. Because you're not measuring the voltage versus the counter electrode, you're measuring the voltage versus the reference electrode. So you can drive whatever reaction you need to at the counter electrode to keep the current. Remember, current has to flow in a circle. If electrons are moving in a circuit, ions have to move in the electrolyte. So you can do whatever reaction you need, but you can measure now only the reaction at the working electrode selectively in this process. So that's why we really like to use potentiostats, okay? So what would now the current voltage curve look like? Okay. So what would the current voltage curve look like? And this is going to be volts versus SHE or NHE. This is going to be current. And, you know, this is going to be negative current. This is going to be plus voltage. This is going to be positive current. This is going to be minus voltage. Okay, so now if I apply a voltage negative to my platinum working electrode versus the standard hydrogen potential in this cell, what's going to happen? How much voltage do I need to apply versus the reference electrode? And remember, the reference electrode is in some ways arbitrary. We've chosen here to use a standard hydrogen electrode, okay? So that sets our voltage scale on the x-axis. So if I, sorry, this would be negative voltage over here, positive over here. This is the sort of backwards nomenclature for, or standard sign convention for current and voltage that Barton Faulkner uses for historical reasons. We typically flip the axis in the research lab. But it's good to be, again, familiar with both. So if I apply potential negative the standard hydrogen electrode, what's going to happen? Do I need 1.23 volts to get current? No, I actually don't. I'll see current sort of immediately, and that will be hydrogen evolution reaction current. And I'll measure some overpotential there, and that's going to be solely due to the overpotential of driving the kinetics of the hydrogen evolution reaction, plus IRU now, which this is going to be called the uncompensated series resistance, which we'll talk about. Okay. Now, if I apply a potential the other direction, right? If I apply a potential the other direction, positive of the standard hydrogen electrode, well, I'm going to drive some current, and that's going to be hydrogen oxidation reaction, right? So at zero, I'm in equilibrium with the hydrogen electrode, right? And so at zero, there's going to be no current because this solution is sort of at the hydrogen evolution reaction potential. It's at the standard hydrogen electrode potential because I have H plus and H2 in their standard states. So here I'm going to oxidize hydrogen. So this is going to be driving H2 goes to 2 electrons plus 2H plus, right? And this is going to be HER, 2H plus, plus 2 electrons goes to H2. So I'll drive those two reactions. So now I have a way to study hydrogen electrochemistry, right? But what happens if now I keep driving this out to 1.23 and beyond? Well, at some point, now I can oxidize something else, right? Now I can actually do oxygen evolution reaction. I can oxidize water. And guess what? Now I can measure here eta OER plus IRU. There's always this uncompensated series resistance term, and we'll talk about that, how to correct for that. So this is really neat. So now in a single experiment, I can measure HER, I can measure HOR. By the way, why is this HOR current flat over this whole region? Well, this is called the limiting current. And it has to do with the fact that there's H2 in solution, but there's not very much of it. So this current you measure here is controlled completely by how fast it can diffuse through the surface, how fast it can get to the surface while you're doing this reaction. And we'll talk about limiting currents in the next week here. Okay, and then and OER, all on the same experiment. And we do it all versus the standard electrode. So if I think about an energy level diagram, I have E, we'll call it HER. So that's sort of our standard hydrogen electrode. And now I can move, this is in solution, this is sort of what the energy of the electrons in solution are set by the hydrogen and proton couple. And now I can move my electrode up or down, right? And I can either put electrons this way, or I can make the electrons go back, and then I can eventually lower the electron energy so much that I can pull electrons out of the oxygen evolution by the oxygen evolution reaction, by pulling them out of water. So we'll get into this and we'll go through this in many more contexts, but this is sort of the overview of why we use a 3-electrode potentiostat. Thank you. I'm looking forward to chatting with you again soon.